A large number of experimental investigations and molecular simulations have demonstrated that adsorption of mixtures such as carbon dioxide and methane, carbon dioxide, nitrogen, carbon dioxide, propane in 13X zeolite exhibits strong thermodynamic non-idealities, and mixture adsorption equilibrium is not adequately described by the ideal adsorbed solution theory. The objective of my presentation today is to demonstrate thermodynamic non-ideality effects in ternary mixtures in 13X zeolite. I specifically consider ternary mixtures of carbon dioxide, methane, and nitrogen, carbon dioxide, methane, and propane in cation exchanged zeolite, NaX, whose trade name is 13X. Typically, this consists of a unit cell in which we have 106 silicon atoms, 86 aluminum atoms, and 86 extra framework sodium cations, shown here with the blue spheres. The silicon to aluminum ratio is 1.23. The cages of 13X or NaX zeolite have a diameter of about 11.5 angstrom. Each cage is connected to adjacent cages by a window or whose aperture is 7.4 angstrom. From the computational snapshot shown here for mixtures of carbon dioxide and methane, it is visually evident that CO2 tends to locate preferentially near the extra framework cations, and this results in an inhomogeneous distribution of guest adsorbates within the pore landscape. I refer you also to my earlier video presentation on segregation and congregation effects in CO2 capture with NaX zeolite. In order to demonstrate the inhomogeneous distribution of guest adsorbates within the pore landscape of NaX zeolite, let us examine the radial distribution functions for mixtures of CO2 and methane at a total pressure of 100 kilopascal and a temperature of 300 Kelvin. The radial distribution functions have been determined using configurational bias Monte Carlo simulations. The red curve shows the distances between CO2 pairs. The blue line indicates distances of CO2 from the extra framework cations. The green line shows the distance of separation between pairs of methane molecules, and the black line shows the distance of separation between CO2 and methane. We note that the maximum in the CO2 paired distances is quite close to the maximum in the distances between CO2 and the extra framework cation. This implies that CO2 is located close to the extra framework cations or congregates around the sodium cations. If you look at the black line, It shows the distance of separation between the guest adsorbate CO2 and methane, and this is significantly higher. For example, the maximum occurs at 4.5 angstrom compared to 3.2 angstrom for CO2-CO2 pair. So the methane molecule is further away from the CO2 than is the case if the guest adsorbates were to be homogeneously distributed. This non-homogeneous distribution leads to deviations from thermodynamic non-idealities. The same is true for mixtures of CO2 and propane. The distance between CO2 and propane molecules indicated by the black line is significantly larger than the distribution between two CO2 molecules. So the propane molecules are located further away from the CO2 molecule, leading to segregation. The same holds for CO2 nitrogen. The distance between CO2 and nitrogen is typically larger than the distance between CO2 and the extra framework cation sodium. So CO2 congregates around the extra framework cations, and the partner molecules, be it methane, be it propane, be it nitrogen, are further away from CO2, and therefore the competition between CO2 and the partner molecules is significantly lower than that anticipated by the ideal adsorbed solution theory that mandates a homogeneous distribution of guest adsorbates. The key tenets of the ideal adsorbed solution theory are summarized here. All the adsorption sites within the microporous crystalline material are equally accessible to each of the guest molecules, implying a homogeneous distribution of guest adsorbates within the pore landscape. No segregation, congregation, or preferential siting of any of the guest species in the mixture. No change in the specific surface area of each molecule on mixture adsorption. This implies that a guest species occupies the same surface area on the host framework, whether it is present on its own or in the company of partner species. On the basis of these tenets, the partial fugacity of each of the species I in the bulk fluid phase is written as being equal to the sorption pressure times the mole fraction. This is an expression that is precisely analogous to the Raoult's law for description of vapor-liquid equilibrium. In the event of failure of one or more of these tenets, this expression does not hold any longer, and we need to introduce activity coefficients in this expression to describe deviations from the ideal adsorbed solution theory. The introduction of activity coefficients results in the real adsorbed solution theory, For a further description of the theoretical background, I refer you to my publication in ACS Omega in 2021. Watch also my presentations on the IAST and the RAST on my YouTube channel. With this background, let us examine experimental data on CO2 nitrogen mixture adsorption in 13X zeolite. Due to congregation of CO2 around the extra framework cations, the IAST estimates of the adsorption selectivity for CO2 methane mixtures is significantly higher than those determined from configurational bias Monte Carlo simulations that are indicated by the symbols. We conducted 3 types of CBMC simulations. In one set, the total bulk gas phase fugacity was held constant at 100 kilopascals, and the composition of CO2 in the bulk fluid phase mixture was varied between 0 and unity. And we see that the adsorption selectivity for CO2 with respect to methane is significantly lower than the selectivity anticipated by the ideal adsorbed solution theory. This is because the competition between CO2 and methane is significantly lower than the anticipation of the IAST. This lowering in the selectivity is a consequence of congregation of CO2 around the extra framework cations. So IAST overestimates the adsorption selectivity. 2 other types of CBMC simulations were carried out. The blue triangles are the simulations for 50-50 mixtures of CO2 and methane, and the total fluid phase fugacity of the bulk mixture was varied from low values to near pore saturation. Again, we note that the adsorption selectivity determined from molecular simulations, when plotted against the surface potential that serves as a proxy for the spreading pressure, is significantly lower than the estimates of the IAST for both 50-50 mixtures and for 595 mixtures indicated by the inverted pink triangles. For the 3 sets of CBMC simulations shown on the foregoing slide, we can calculate the activity coefficients in the adsorbed phase for each of the guest adsorbates, and these activity coefficients are plotted for the first set of simulations, in which the total fugacity is maintained constant at 100 kilopascals as a function of the mole fraction of CO2 in the adsorbed phase mixture. As the mole fraction of CO2 in the adsorbed phase approaches unity, the activity coefficient should also approach unity. The mole fraction of methane in the adsorbed phase mixture is unity at this point here, and the experimental data, or in this case the simulation data, when extrapolated, should also approach unity. If you look at the other sets of CBMC simulations in which the mixture composition in the bulk fluid phase is held constant and the surface potential is increased. We note that the activity coefficients of each of the gas molecules tends to unity as the surface potential tends to 0. This is because a surface potential of 0 implies a pore occupancy that is vanishingly small, and the activity coefficients of both adsorbates must tend to unity. In order to set up the appropriate model to describe the variation of activity coefficients with the adsorb phase compositions x1 and x2 and the surface potential, we need to introduce the correction factor 1 minus exponential minus a constant c times the surface potential phi. This factor is a representation of the pore occupancy. This ensures that as the pore occupancy approaches 0, ln gamma of component 1 and 2 both approach 0, and therefore gamma of the activity coefficient of each of the gas adsorbates tends to unity. It is absolutely of vital importance to introduce this correction factor into the model to describe the variation of activity coefficients with adsorb phase composition and the surface potential. The same holds for the NRTL model, the Margulis model, etc. All of this background theory is described in my paper published in ACS Omega in 2020. Let's examine now binary mixtures of CO2 and propane. 3 CBMC simulation campaigns were conducted. The first one at a total bulk gas phase fugacity of 1 megapascal, and the composition of CO2 in the bulk fluid phase was varied from 0 to unity. These are the results obtained from molecular simulations for the adsorption selectivity of CO2 with respect to propane. We see that the increase of CO2 in the bulk fluid phase mixture results in a decrease in the adsorption selectivity of CO2 with respect to propane. The IAST estimates are shown by the dashed lines, and the IAST predicts a trend that is the inverse of the trend that is actually observed. So the composition dependence of the adsorption selectivity for mixtures in which the total fugacity is held constant, the trends are incorrectly estimated or predicted by the IAST because of congregation of CO2 around the extra framework cations. In 2 additional simulations shown here for 25-75 mixtures and for 50-50 mixtures, we plot the CO2 propane selectivity as a function of the surface potential that serves as a proxy for the spreading pressure. We again see that the IAST generally tends to overestimate the CO2 propane adsorption selectivity as compared to the molecular simulation results. We also carried out CBMC simulations for CO2, methane, propane mixtures in the proportion 10, 70, 20, and the component loadings of CO2, methane, and propane are plotted as a function of the surface potential in these graphs, and the CBMC simulation results are shown by the symbols, and the dashed lines are the IAST estimates. We note that the IAST fails to provide a quantitatively correct estimate of the loadings for each of the three guest adsorbates, because thermodynamic non-idealities influence the loadings of all three guest molecules. The activity coefficients determined from CBMC simulations here are plotted against the surface potential. We noted that as the surface potential tends to 0, all three activity coefficients tend to unity, and therefore, as I had previously mentioned, it is important to introduce a correction factor that correctly describes the influence of the surface potential on the activity coefficients. Recall that the surface potential is a proxy for the pore occupancy. We also carried out CBMC simulations for ternary mixtures of carbon dioxide, methane, and nitrogen in NaX zeolite at a temperature of 300 Kelvin. The ratios of the three guest adsorbates, CO2, methane, and nitrogen, in the bulk gas phase mixture was held constant at 20, 40, 40, and the total fugacity was increased from very low values of say 1 Pascal to high values of 1 megapascal, indicating approach to pore saturation. The component loadings for CO2, methane, and nitrogen are plotted as a function of the surface potential. The CBMC simulation results are shown by the symbols, and the dashed lines are the estimates of the ideal adsorbed solution theory. The strongest adsorbing component, which is CO2, due to electrostatic interactions with the extra framework cations, is the component loadings of CO2 are in good agreement with the IAST estimates. However, for the partner molecules methane and nitrogen, the IAST estimates are in significant variation with the IAST estimates. The activity coefficients in the adsorb phase for each of the three guest molecules is plotted as a function of the surface potential, and we again note that as phi, the surface potential, approaches 0, the activity coefficients of all three guest adsorbates approach unity. The CBMC simulation data are reported in my paper published in Journal of Membrane Science in 2022. I show here CBMC simulation data for mixtures of CO2, methane, and nitrogen in the proportion 5, 25, 70, and the bulk fluid phase fugacity is increased from low values of say 1 Pascal to about 1 megapascal, at which pore saturation is approached. We again note that the CBMC data for CO2 loadings is in good agreement with the IEST estimates, but for the partner molecules methane and nitrogen, the IEST estimates are lower than the actual CBMC data on the component loadings, because the partner molecules suffer or experience less competition with CO2 than is anticipated by the IEST, that mandates a homogeneous distribution of guest adsorbates in the pore landscape. The activity coefficients of each of the guest molecules tends to approach unity as the surface potential is approaching a value that is vanishingly small, implying a pore occupancy that is negligible in magnitude. With increasing pore occupancy, the activity coefficients deviate from unity for methane, green squares, nitrogen, blue triangles. The message emerging from this video presentation is that the congregation and segregation effects that are prevalent for CO2 capture from methane, nitrogen, and propane leads to strong deviations from the estimates of the ideal adsorbed solution theory. Thermodynamic non-ideality effects are of vital importance in carbon capture applications using cation exchange NaX zeolite.